So far in calculus, we have looked at the addition and subtraction rule of functions when we're deriving functions, also the product rule for when we are multiplying two functions, and the quotient rule for when we are dividing two functions. Today we're going to have a look at what happens if we have a composite function like this. We can see here that essentially we've got two functions. If we remember the rules of BIDMAS, the first function we've got here is 2 minus x. It's inside the brackets, and then essentially the second function is something cubed. So the first stage in using the chain rule to differentiate this is actually identifying these two functions. So what we're going to do is label the outside function here, this something cubed. We're going to say that is ux. So ux is just something x cubed. And then the function inside, we're going to label that v of x, which is just 2 minus x. So we've got this composite function, which we should recognize, u of v of x. So that means we do this first, according to the rules of BIDMAS, and then we apply our second function, u of x, here. So what I want you to do, and this should be a useful revision activity for binomial expansion, is to actually expand this expression and then differentiate each term. So just have a go at that now. Right, so if you actually expanded this, you would have found that A, it takes quite a long time and is not particularly convenient way of differentiating this, but you should have ended up with this. Negative x cubed plus 6x squared minus 12x plus 8. If you differentiate that, just using the rules we've looked at before, it's minus 3x squared plus 12x minus 12. What I want you to think about now is what happens if we take this function here and we differentiate it using the power rule. So, if you do that, how does that compare to the answer that we've found up here? So just to reiterate, take our expression f of x equals 2 minus x cubed, differentiate it using the power rule that we've looked at and expand, and see how your answer compares to the derivative that we've just calculated. And then once you've done that, just have a think about what you might have to do to your answer from this to end up with this. So here is our function. If we use the power rule to derive and then expand, we can see that's going to be 3, bring the power down and subtract 1 from the power. That's going to be 3 times 2 minus x squared, which is going to give us 3x squared minus 12x plus 12. Now if you look back at what the actual derivative is, we calculated this the kind of old school way, you'll notice it's not quite the same. So what have you got to do to get from here to here? Well, you should be able to see that you've just got to multiply that by -1. Now just think and see if you might be able to figure out where that -1 comes from. Right, let's have a look at another example. So here, expand and differentiate this. So 3x squared plus 1 all squared. So again, first of all, what I'd like you to do is just try and expand and then differentiate this using the tools that we already have, so the power rule. Once you have found the derivative, what I want you to do is to try and again see if we can find a shortcut. So apply the power rule to differentiate this, and then try and figure out what you need to do in order to actually get to the correct answer, which you should have found from here. So if you expanded and found the derivative correctly, you would have found that fx is 9x to the power 4 plus 6x squared plus 1. So if we differentiate that, we get this, 36x cubed plus 12x. Now that is the derivative. If we use the power rule to find the derivative, we can see that we would end up with this. Bring the power down in front, so 3x squared plus 1, subtract 1 from here, leaves us with that. So the derivative would be 6x squared plus 2, which is not the correct answer. Yeah, we've already found that this is the correct answer. So how can we get from here to here? Well, we should be able to see that to get from here to here, we need to multiply it by 6x. So where does that 6x come from? Well, we should be able to see that if we actually differentiate what's inside the brackets, that will give us 6x. And this is essentially what underpins the chain rule, which we'll have a look at in more detail now. So the chain rule formalizes this, and it says if you have a composite function, so u of v of x, then the derivative is u dash v of x, so the derivative of u of x, multiplied by v dash x. So in effect, we can phrase this as the derivative of the function on the outside multiplied by the derivative of the function inside. So here are three examples. Let's have a look at the first one together, and then you can have a go at the second two yourself. So we've got a function f of x. We know it's a composite function. It's 4 brackets 5x cubed plus 2 all to the power 6. So just like we looked at previously, we've got two functions here. So the first function is going to be u of x, which is on the outside. So we've got 4 times something to the power 6. So that's going to be our u of x. So our function on the outside. Our first function here is going to be 5x cubed plus 2. So that's our function on the inside. So v of x here, 5x cubed plus 2. So what our chain rule says, and again, if you really wanted to, you could expand this all and differentiate, but hopefully you can see that would be horrendous here. So using the chain rule, what we're going to do is find the derivative of the function on the outside and multiply that by the derivative of the function on the inside. So what's that going to look like here? Well, our function on the outside is this, u of x. So u of x equals 4x to the power 6. So if we find the derivative, if we differentiate this, this is going to be 6 times 4, which is 24x to the power 5. However, we actually know what x is, don't we? X here is actually 5x cubed plus 2. So we're going to say that the derivative of the function on the outside is 24 times 5x cubed plus 2 to the power 5. However, as we saw in the previous examples, that is not quite right. We also need to multiply that by the derivative of the function on the inside. So the function on the inside is 5x cubed plus 2. The derivative of this then is 15x squared. So if we multiply that, that will give us the solution. So what I want you to do now then is just have a look at question B and C and try and have a go at those by yourself. For question B then, we can see first of all that it's not very helpful to express it using a square root sign, so we're going to express it as a rational exponent, which is just 4x squared plus 1 to the power half. So here to find the two functions, u, our function on the outside, is some value to the power half, v of x is the bit in the inside, 4x squared plus 1. So the derivative is going to be, first of all, differentiate this, so half x to the power negative half, but we know what our function in the middle is, it's 4x squared plus 1, so that goes there, it doesn't change, but when we multiply it by the derivative of this, which is just 8x. That is going to give us 4x over 4x squared plus 1 to the power half, because in this context negative means 1 over, which you could rewrite as 4x over root 4x squared plus 1. For part C then, here not immediately obvious, but your two functions are going to be u of x equals e to the x, so some value as a power of x, and v of x is going to be what is actually in here, which is x squared. So in this instance, the derivative of the outside with respect to the inside function. So here we've got e to the x squared. So here we've got u of x equals e to the x. We should remember that when we differentiate this, it stays the same. So this is just e to the x, and we know that the function on the inside is x squared, so that's just going to be e to the power x squared, multiplied by the derivative of what's inside, which is 2x, and that's going to give us this, 2x e to the x squared. So, final question in this little section here is the first two parts of an exam question. So we've got some function here, fx equals 6x over x plus 1 for x is greater than 0. So I want you first of all to find the derivative of this, and then secondly, we've got this function here, let gx equals ln 6x over x plus 1 for x is greater than 0. So show that the derivative of this is 1 over x brackets x plus 1. So I'll give you a little time to try and work those out, and then we'll go through it. Okay, so part A. Hopefully you will have recognised that this is not the chain rule. Here you are dividing one function by another, so we're going to be using our old friend, the quotient rule. For this first mark, you needed some evidence that you were using the quotient rule, ideally. In theory, you could have used the product rule, but let's just go through the quotient rule. So u dash v minus u v dash all over v squared. So you only had to get it in that form, you didn't have to substitute it incorrectly for that point. The next two marks are evidence of correct differentiation. So we can see that for here, if we want to get u dash v minus u v dash, we've got to actually figure out the correct values for u dash and v dash. So here we can see that if we differentiate 6x, it gives us 6. If we differentiate x plus 1, it's just going to give us 1. So correct differentiation, 1 mark for each of those. Now, to get the next mark, you have to substitute that in correctly into the quotient rule. So we can see it's going to be x plus 1 times 6 minus 6x all over x plus 1 squared. We can expand and simplify, and we'll end up with this. The derivative is 6 over x plus 1 all squared. For part B then, let gx equals ln 6x over x plus 1 for x is greater than 0. Now, when we looked at the derivatives of ln, we saw that if we had ln x and we differentiated it, the derivative would simply be 1 over x. And we're being asked here to show that the derivative equals this. Here, we're going to have to use the chain rule because we've got, in effect, two functions. So here, the function on the outside would be ln of x, and here the function on the inside, vx, would be 6x over x plus 1. So what you've actually got to do then is differentiate ln x, so that would be 1 over x, but we know that x, our function, is actually 6x over x plus 1. And then we're going to multiply it by the derivative of what's inside here. Now we saw in part A what the derivative of this was using the quotient rule, and it was 6 over x plus 1 squared. So this would be the evidence that we're using the chain rule. You get 1 mark here for recognising that the reciprocal of this is just x plus 1 over 6x. Working that clearly to the answer, so we can see that when we flip this, it's going to be 6 times this is going to be on the top, x plus 1, all over 6x times x plus 1 squared, and we can see that this will cancel out to give us g of x equals 1 over x brackets x plus 1, which is what we were asked to show in the question.